Alright, so let's just look real quickly at one kind of interesting application of linear equations, or systems of linear equations. And it has to do with curve fitting. Now, curve fitting is the idea that you take some points um, that you've plotted. Now, right here, I'm just plotting, a few random points, right? Well, not random, but I guess I'm just plotting a few points. So negative 1, 4, 1, 2, 2, 1, and sorry, that was not 2, 1, 2, 1, and 3, 16. We'll put it up there. So you take some points, and the question is, can you find a polynomial that goes through those points? Right? Can you find a polynomial that goes through those points, and of course the associated equation? Now, the reason this is important is because where this happens in real life is the points that we have, that we start with, are data. They could be data that we collected. Maybe they're population sizes, maybe they're times and places, or times and measurements. Whatever they are, but they could be real data. And so the question is, can you find an equation that fits them, that goes through them? And if you can, then what you've found is a mathematical model, a mathematical equation that at least attempts to describe the situation. Okay? So that's why this is kind of important. And we're just going to keep it real simple here. We're just going to take a few points, and we're going to ask, let's find a polynomial. And we're only going to deal with polynomials here. Find the polynomial of smallest degree. Find the polynomial of smallest degree. Okay, so if we can do it with a degree 5 polynomial, we don't want to do it with a degree 7 polynomial. We want the smallest degree. That we'll use this terminology, fits the data, or fits the points, or goes through the points. So can we find a polynomial that goes through those points? All right. So the first rule is this. The answer is you can, and the question is, what should the degree be? And the answer is, the degree is always going to be 1 less than the number of points. So here we have 4 points. So we should be able to find a polynomial of degree 3 that goes through those points. Okay, so y equals a plus bx plus cx plus dx, sorry, that's cx squared plus dx cubed. Okay, there's our polynomial of degree 3. So the rule, the theorem, is that if you have n points, for any n points, you can find a polynomial of degree n minus 1. Well, let's put it this way. For any n plus 1 points, you can find a polynomial of degree n that goes through them. And think about it, right? If you have 2 points, is there an equation that goes through those? Sure, it's a line. That is degree 1, right? A line is degree 1. If you have 3 points, can you find a curve that goes through them? Sure, it's a parabola. That's degree 2, right? 3 points, degree 2. So real simply, that's the idea. So if we've got 4 points, then we should be able to find a polynomial of degree 3 that fits them. If we have 7 points, then we should be able to find a polynomial of degree 6 that fits them. And in fact, it's got to be at least degree 6. If I want to go through 3 points, I have to have at least a degree 2 polynomial. A degree 1 will never work. A line will never work, right? So it gives you the minimum number of the minimum degree to go through those points. It's a really interesting idea. So if for some reason I've got 30 points, 30 data points, and I want to try to model it with a polynomial, I would require a degree 29 polynomial. Okay, so that being said, here's how we write our degree 3 polynomial, which I know is slightly different than what you're used to, right? We're used to writing it in descending order, but when we're having this discussion, we write it in ascending order so that the largest degree is at the end, okay? So let's see how this works. Here are our points, okay? So let's write these down. So we had -1, 4, 1, 2, 2, 1, and 3, 16. Okay, so you're probably already ahead of me on this, but what we're going to do is we're going to use these points to create a system of equations. So, for instance, we'll use the first case where x equals -1, and if you plug -1 in, so it looks like this, a times, or a plus minus, well, we'll write it -1 times b plus 1 squared times c plus -1 cubed times d. That's all supposed to equal y, which is 4 in this case, right? If x equals 1, what does it look like? A plus 1b plus 1 squared c plus 1 cubed d equals 2. Let's plug x equals 2 in. A plus 2b plus 2 squared c plus 2 cubed d equals 1. And lastly, if x equals 3, we get a plus 3b plus 3 squared c plus 3 cubed d equals 16. So we're writing it this way so you can see the pattern start to develop, right? So this leads to this system, right? 1 minus 1 minus 1 squared minus 1 cubed, 1 1 1 squared 1 cubed, 1 2 2 cubed, or 2 squared 2 cubed, 1 3 3 squared 3 cubed, times your a, b, c, d equals your y values, which are 4, 2, 1, and 16. So we get that system. This matrix right here, and this is why we wrote it in ascending order, so that we could easily see the pattern. Look, this row is just going to be the x coordinate of our first point. Not there, that's going to be just 1. But then you have x coordinate to the first power, x coordinate to the second power. Let's do it this way. X coordinate to the first, x coordinate to the second, x coordinate to the third, right? And then 1, x coordinate to the first, to the second, to the third. 1, x coordinate to the first, to the second, to the third. And so you get this nice predictable pattern. So so all we have to do to figure out our equation is to figure out what A, B, C, and D are, is to solve the system, right? Because once you know what A, B, C, and D are, then you know the polynomial that goes through these points, right? And the interesting thing is this matrix right here is always always has that pattern, right? If you're doing a degree 4th polynomial, then you would have everything to the 4th power as your final column. But this is called the Vandermonde matrix. It has some real interesting properties. I don't think we're going to go into them, but if you wanted to, you could explore some of those properties, especially related to determinants. I'll just put this page 218. So in the previous section, 3.6 exercises 61 through about 63. If you wanted to think about some interesting properties of Vandermonde matrices, all right. But in the end, it just turns into a system, right? It just turns into the A matrix is equal to what we have here, and of course we would write it as 1 minus 1 1 minus 1 1 1 1 1 1 2 4 8 1 3 9 27 and then A, B, C, D, and then 4, 2, 1, 6. And then we would solve it. How do we solve this? Remember how we do this? The solutions are going to be the inverse of the coefficient matrix times B. This is A, this is X, this is B. Okay, so I'll leave you to that to solve that. Once you've done that, you'll figure out what A, B, C, and D are, and you end up solving it out, and getting these A equals 7, B equals -3, C equals -4, and D equals 2. And so your polynomial that goes through those points is 7 minus 3x minus 4x squared plus 2x cubed. Okay, so using this approach, you can find a polynomial that goes through any number of points. You just have to have 1 degree less on the polynomial, and of course you have to have all the points, right? So you have 4 points, you're going to give you 4 equations. Okay, and that is some curve fitting.